All right, so now that you know what an acid is, now that you know what a base is, let's talk about the reaction that takes place when acids react with bases. This is what we call a neutralization reaction. All right, so example, HCl, which is an acid, sodium hydroxide, which is a base. The products are going to be water and a salt. Now, the word salt here, it looks like it means sodium chloride, which you know is table salt. But it doesn't literally mean table salt. A salt, the definition of a salt, is an ionic compound that does not have hydrogen ion, hydroxide ion, or oxide ion. Okay, so it has to be ionic, but it can't have H+, because if it was ionic and it had H+, that would make it an acid. It can't have OH-, because if it did have OH-, that would make it a base. And if it had oxide, oxide would also make it a base. All right, so just strictly using that definition, if we have a list of compounds here, the question is, which of the following are salts? So you are looking for an ionic compound that doesn't have H+, so this guy's ruled out because HF, that's an acid. It's got an H placed in the front of the formula. It can't have OH-, so this is out. And it can't have oxide, so this is out. That leaves us with 3 salts. All right, so a salt is an ionic compound. It does not have to be NaCl. It could be any ionic compound with various other elements, as long as it doesn't have those 3 ions. And the other product is water, right? Now, this is your classic double replacement reaction. So you should be familiar with how to predict what the salt is going to be, and the fact that the water is made, well, that's always going to be made. So, okay. Let's look at a couple examples and predict what the products are going to be and then balance them. So let's write balanced neutralization reactions for the following: potassium hydroxide and nitric acid. Now, nitric acid's formula is HNO3. So potassium hydroxide, it's a +1. Hydroxide is -1, so that's going to be KOH. Charges, it's pretty important to check your charges throughout here, this unit, especially during neutralizations, because you might forget, and it's going to change the way they're balanced. So nitric acid, which was HNO3. So if this is your classic double replacement, then you should notice that here, the H+ and the OH-, those two are the sources of your water. That's how you get your water. And that leaves K+ and NO3-. And that formula is neutral, so we're good there. And now we have to balance. And oh, hey, look, we're down. We're done. We're balanced. Here's our water, and here's our salt. Okay. So why don't you guys try the next 2 on your own? See if you can write them and balance them. So what do we think for number 2? First of all, what's the formula for lithium hydroxide? LiOH. And the formula for sulfuric acid is given right here. Notice that this sulfuric acid is diprotic. It's got 2 hydrogen ions that it can give away. Okay. What's one of my products? H2O. Sometimes when we write neutralization reactions, you could write water this way. Just kind of helps you count better, right? Because if you look at this, now you see here's the hydrogen, but notice that there's 2 hydrogens here. So that means you are going to have to probably double this. All right. What's our other product? Lithium sulfate. Now, lithium is a +1 charge. Sulfate is a -2, so don't forget your subscript of 2. Okay, we're almost balanced. One more thing. Let's put a 2 there. And by putting a 2 there, now you see 2 hydroxides, which is where these 2 hydroxides come from. All right, now, writing it as HOA, you don't have to do it that way. You can write water just like normal, but sometimes when we're balancing these, it's kind of easier to show where they came from. So it's not wrong if you write HOH, right? It's kind of like a helpful little tool. Okay. Phosphoric acid, H3PO4. Barium hydroxide. If you checked your charges, you would have seen that barium is a +2 charge, which means it's going to carry 2 hydroxides. Okay. So, water. And if barium combines with phosphate, and the only way that would work is if this is Ba3PO4 2. Okay, so now we balance. We've got 2 phosphates on the right. Let's put a 2 here. That means 6 hydrogen ions on the left, so we put a 6 here. And that means 6 hydroxides, so we put a 3 here, and that fixes the barium also. Okay, neutralization reactions. They're double replacement reactions. That's all they are. You're making water and you're making a salt. So, no big deal there. Okay. So, we need to differentiate between the types of acids because in your lab you actually worked with what's called a strong acid and a weak acid. So let's talk about the difference. A strong acid is one that will dissociate completely. Okay, so what does that mean? So hydrochloric acid is your classic strong acid. Now hydrochloric acid, and I'm going to write this in a simpler form first. I'm going to write it without the water. Hydrochloric acid will separate into hydrogen ions and chloride ions completely. Complete separation. There are other examples of strong acids. There's a list. This will also happen with something like hydrogen iodide. It'll break up into H plus and I minus. So imagine if you had 1,000 molecules of hydrogen iodide. That means once you mix them into water, oh, I should specify this is in water. if you had 1,000 molecules, you would end up with 1,000 hydrogen ions and 1,000 iodide ions. They would all break apart. That's what a strong acid is. And the reason why it's called a strong acid is because it produces the greatest concentration of H+. Every single molecule produces an H+. So therefore there's more H+. The more H+ there is, the more acidic it is, so it's like a stronger acid. Okay? Now, let's contrast that. A weak acid dissociates partially. All right? Hydrofluoric acid, I'm going to simplify this equation. I'm going to rewrite it again. HF will break down, and you will get H+, and you will get F-, but this is going to be incomplete separation. So what that means is, if we started with 1,000 molecules of hydrogen fluoride and I mix these into water, I might only get 30 hydrogen ions, 30 fluoride ions, and then the remainder, the 970 hydrogen fluoride molecules that are left, will not break apart. So the vast majority of molecules stays intact. Only a small percentage actually break apart, which means you don't get a lot of H+, and that's why we call this a weak acid. Are you guys seeing the difference here? Let's put this into numbers, right? So, another example. So, let's say HBr is a strong acid. And let's say, this little chart here shows the concentration at the beginning and at the end. So let's say at the beginning my HBr concentration is 1 molar. And we don't have any of the H+ or Br- yet. At the end of this reaction, all of this acid will break apart. And then you're going to have 1 molar H+ and 1 molar Br-. There's nothing left of this because it all broke apart. That's a strong acid. But if we look at a weak acid, like cyanic acid, HCN, and I draw the same table for this, and if I start with the same numbers, so 1 molar there. Okay. In this situation, I might get 0.001 molar of H+, and I might get 0.001 molar of Cn-, which means when this reaction is done, I'm going to have 0.999 molar HCN. A very small percentage of weak acids actually produce H+. So they're going to be less acidic. That's why weak acids are generally not dangerous, whereas the strong acids are the ones that, we take more care handling. All right, do you guys understand the difference? Weak versus strong acids. So, there's a list here of the strong acids. Perchlorate, you don't have to memorize the names, right? But you do have to memorize the formulas. You will have to know these formulas here. HClO4, HCl, HBr, HI, HNO3, H2SO4. Now, you might find a little trend here with these guys. What do they have in common? Yeah, they all have halides in them, right? HCl, HBr, HI. The Cl, the Br, and the I are all from the same family. So those three you can kind of memorize pretty quickly. It's just the other three that you have to take some time to commit. Perchloric, HClO4, HNO3, H2SO4. Okay, so If these are the only strong acids, that means anything else with an H in front must be a weak acid. In your lab, you used HC2H3O2. That's known as acetic acid. That's a weak acid. How do we know it's a weak acid? Because it's not on your list of strong acids. H2SO3. That's a weak acid. Careful, it looks like H2SO4, but it is different. The formulas matter. Okay, so those are strong acids. These are the ones that ionize completely. All right. Here's a picture. On the left, we've got a strong acid. If I mix HCl into water, the only thing that there is in water is H plus and Cl minus. And notice how they're all separated. But carbonic acid, which is used as, it's found in soda pops. When I mix this into water, there's a good proportion of these that are still intact. They're still together. They did not separate, whereas a couple of these did separate. So, weak versus strong. Based on this, if I took a conductivity tester and dipped it in each of these beakers, which one would light up brighter? Yeah, the strong acid. Strong acids, strong electrolytes. They're better electrolytes. They conduct more. How come they conduct more? There's more ions moving around. All right. This other picture is not as easy to see. So this picture is a better picture. Okay, let's talk about bases. What's a strong base? Strong base is one that dissociates completely. Sodium hydroxide. Now notice in a dissolving equation how we have water on both the left and right side. Algebraically, that's redundant. So for bases, we just write it as NaOH, arrow, and then the two ions. This is a base because it produces hydroxide, and it's a strong base because it dissociates 100%. The common strong bases are listed here. Notice there's also patterns. Sodium hydroxide, potassium hydroxide, lithium hydroxide, find them on the periodic table. LiNAK. And then barium hydroxide, strontium, and calcium hydroxides, find those on the periodic table. Notice on the periodic table it makes kind of like a little pattern like this. So if we take those hydroxides, those are going to be our strong bases. Okay, so you do have to memorize these. You will have to know them over time. All right. The sooner you memorize them, then the faster this will come to you, and then the rest of the unit will be easier. Right? If you put off memorizing these till the end of the unit, you're going to kind of struggle a little bit through this unit. Okay, so just try to memorize them as soon as you can. All right. So let's talk about water for a second here. Water molecules will often collide with each other. And when they collide with each other, these are the two products. But first, I need to talk a little bit about hydronium. And I don't know how good of a job I did earlier. So let me just insert a page here. Okay. Back to acids for a second. So we discussed how when there's a strong acid, it breaks off into HCl and Cl minus. Here's the thing. The H plus ion does not exist by itself. it immediately attaches to water. So what happens is H plus bumps into a water molecule. Remember how the oxygen side is negative? So the result of this is we have what's called hydronium. And the formula for hydronium is H3O plus, because it's water that has gained a hydrogen positive ion. So anytime I say that H plus is produced, because we're always talking about water, in reality it's not H plus that's floating around, it's really hydronium that's floating around. But you will see questions still asking about hydrogen ion or hydronium, and for all practical purposes, whatever concentration of H plus there is exactly the same as the concentration of hydronium. So what I'm saying is they're interchangeable. Okay? If I give you the concentration of hydronium, it really means the concentration of hydrogen ion and vice versa. Because hydrogen ion itself is immediately bonded to water. It does not exist by itself. It's impossible for it to exist by itself in water. It just latches on right away. Okay, so that's where this H3O plus business comes in. Now, going back to an earlier reaction that you saw, when I first showed you the reaction for HCl, there was water in that equation. And that's because we were showing the formation of hydronium. These two equations are the same. The only difference is one of them included water, and as a result you see hydronium form, and the other one does not include water, and that's why there is no hydronium. That's why it's just H+. But the point is they're equivalent. So when you write an equation with water, you don't need to include the water. If you have an acid, you can leave it out. It's okay. Or you can include it, and it's fine too. But don't be thrown off if you do see it there, because if you do see it there, it's perfectly acceptable. Okay. So, back down here. Water molecules, when they bump into each other, one water will take the hydrogen from another. So if these two collide towards each other, they bump into each other, one of them could end up with 3 hydrogens and the other one will end up with only 1. And this happens frequently. That's why we have H3O plus and we have OH minus. So, what that tells us then is that H plus and OH minus both exist in water. That means water contains both an acid and a base at the same time. Now, water, though, is neutral. When you drink water, you're not afraid of it. It's not going to burn you, right? It doesn't feel slippery. It's not going to, like, dissolve things. It's because the H plus and OH minus are present in the same concentration, so they cancel each other out. Right? So, they are made in equal proportions. That's why water is neutral. All right. So that's a little weirdness with water, but the reason why we need to talk about that is because of what's called the pH scale. The pH scale is what we use to measure how acidic or how basic something is. So, first of all, what the pH scale is based on H plus or hydronium, right? Because remember I said H plus and H0 plus are numerically equivalent. There's also what's called the pOH scale. pOH, OH, as in for bases, right? H as in for acids. Okay, let me, here, let's just run through the formulas. I'm going to run down here to the bottom, and then I'll run back up to the top. This is your first equation. When I want to calculate the pH of something, the pH scale is what we call a negative logarithmic scale. It's a power of 10 scale, but when we say it's a negative logarithmic, that means as the concentration of something goes up, the value of the pH goes down. So, just to give you a little chart here. Because the pH measures the concentration of H+, when the concentration of H+ is 1 molar, so remember brackets mean molarity. When the concentration of H+ is 1, if I take in my calculator negative log of 1, and by the way, everyone know your log key is? It's in the left-hand side. Right, so the negative sign is at the bottom. It's not the subtract key. It's the negative sign key. So negative log 1. Enter. That would give us a pH of 0. Okay, let's make the concentration of H+ smaller. Let's make it 0.1 molar. So negative log 0.1 gives us a pH value of what? 1. Let's do another value, 0.01. Negative log 0.01. What's the pH value? Okay. And this goes on in similar fashion. So what you should be noticing here then, as the concentration of H+ decreases, the pH value increases. Right? The most acidic solutions you saw in lab were the ones with the lowest pH values. Okay? All right. So, what if you have the H+ concentration but need to find the pH value? Well, this is your second equation. This is the inverse operation of that. When I say inverse, but it's not literally mathematically inverse. I just mean it's the way of going back. Okay, so let's say I have a pH of 3.55. If your pH is 3.55, what you would do is you would take, to find your H+ concentration, 10 raised to the negative 3.55. It's 10 raised to the negative 3.55. So if you do this right, your concentration of H+ will be 2.82 times 10 to the minus 4. Check and make sure that you're getting the same value as me. You need to know how to do these operations. Let's do another one. Let's do a pH that is lower. So when the pH is 1.25, the H+ concentration will be, and so let's go ahead and carry that out. So 10 raised to the negative 1.25. What do you get? Okay. So what happened here? When you started with a pH that's 3.55, this is your concentration of H+. But when you have a much lower pH, your concentration of H+ is higher. Makes sense. The lower the pH, the higher the concentration of hydronium. You will not have to memorize these equations, by the way. Right, we'll give them to you. They'll just be right there on the front of the test. Okay, so that's what you do when you have either the H+ concentration or the pH value. Now, let me jump backwards a little bit because I kind of back here in acids, your pH is less than 7. In bases, your pH is greater than 7. In a neutral solution, the pH is going to be 7. So regular water is the pH is 7. So let's think about that for a second. A pH of 7. If I know the pH is 7, what is my concentration for H+? It would be 10 to the negative 7. So that's weird. Let's look at this chart here. In any aqueous solution, whether it's an acid or a base, you have both H+ and OH-. They're both present at the same time. The question is, which one has the higher concentration? So, in 1 molar HCl, the concentration of H+ is 1. The concentration of OH- is really small. It's 10 to the negative 14. So if these pHs should make sense, as we make the concentration of H+ smaller, the pH goes up. Now right here, 7. 7 is neutral. And so therefore the concentration of H+ should be 1 times 10 to the negative 7. We just solved for that. And then, as the concentration of H+ gets even more remote, these numbers go all the way up. So, there's 2 scales at work here. There's the pH scale, and there's a second scale. It's called the pOH scale. And the pOH is calculated similarly. The only difference is, if it's the OH concentration that you are given, then the only thing that you can solve for is the pOH. So basically you have to work with what you're given. If you're given the OH- concentration, you can find pH. Now, this equation ties the two together. Once you know the pOH, then you can find the pH, because the sum of these two adds up to 14. Okay. So let's go back this example we did over here, right? If the pH is 3.55, I could ask you, well, what's the pOH? To find the pOH, you would just subtract 3.55 from both sides, and you would get 10.45. The pOH is 10.45. If you have the pOH value, you can find the OH- concentration, because this equation and this equation are related in the same way that these two are related. So whichever equation you use first depends on what value you are given first. But ultimately, you can use one value to find all of the others. Okay, so let's make sure that we know how to calculate with these. So if we have an H+ concentration of 3.2 times 10 to the negative 5th, find the pH. Pick a formula on the previous slide, whichever one you think will help you. What do we get? Okay. Is that lake acidic or basic? That's acidic. And this is actually pretty common, right? Lots of groundwater is acidic, right? Because the carbon dioxide absorbs into water, and carbon dioxide ends up forming what's called carbonic acid, and that means it's just slightly acidic. The water here in this area actually is pretty acidic too. So if I went to any one of our taps in the building and took a beaker and filled it up with water, and then I used the pH probe, the pH reading would be about 5.5. That's very common in this area. No, you will not really find water that comes out of the ground that is a pH of 7, unless that water has been conditioned. Conditioned meaning like filtered, or like, you know, stuff removed from it. Okay, number 2, the Des Plaines River measures pH of 7.9, Des Plaines River is downriver from a bunch of factory runoff, by the way. Okay, what's the H plus concentration in this case? What do we get? Okay. Coke, as in the beverage, has an H plus concentration given there. I want you to find both of these values. I want you to find pH and pOH. So what's our pH? 3.43 or 3.44, I guess, with rounding. Okay. And that means the pOH would be what? Okay. Okay. Take a few minutes and do the last three, and we will check. All right. So for blood, if you're given H plus concentration, we can find the pH. We get a pH of 7.34, which is above 7. Remember 7 being neutral. This is slightly basic. In fact, all of your bodily fluids have a pH of about 7.4. Right? Your tears, your blood, your lymph. It's just the proper pH for all of your cellular functions, right, to maintain homeostasis. Number 5, baking soda. If you're given the concentration of OH minus, the first thing you can solve for is POH. So you take the negative log of that. You get a POH value of 5.11. And then to find the pH, it's going to be subtracted from 14, pH of 8.89, which is basic. And in number 6, barium hydroxide is dibasic. I use that term because the barium hydroxide has 2 hydroxides on it. You get 2 hydroxides per formula. That makes sense? Dibasic, okay? So you have to account for that here. 2 hydroxides per formula, which means your concentration of hydroxide is really 0.0007. Then take the negative log, get your POH, and then subtract from 14, get your PO, or then you get your pH. How are we doing, guys? pH calculations, the lower the pH, the more acidic, the higher the pH, more basic. On the POH scale, a low POH means what? Basic. Yeah, so it's inverted. Okie doke. Let's say we're done.